Welcome students, welcome to the next session of structural analysis 2. So today is our new chapter, it is regarding matrix analysis of the structure. Till now we have done so many methods for analyzing any type of structure. There we have observed Canis one time, moment distribution method one time. In previously we have went for some slope deflection methods. So each method is giving some outputs for analyzing an indeterminate beam or a frame. Okay, so involving all those things, as we have observed, that becoming very lengthy. Okay, so for reducing our length, I am using a combination of mathematical introduction into our structural analysis, which is using the matrix methods. So in this chapter we are not completely going into the matrix analysis because that chapter will be in your post-graduation studies. So here the chapter itself is having introduction to the matrix methods. In that, two matrix methods will be there. First one is flexibility methods and then the stiffness methods. In the flexibility methods, we will observe introduction, application of the flexibility method to the continuous beam which are having two unknowns, highest of two unknowns. Okay, more than that, the structure becomes even more complicated. That we will give you for the post-graduation or the next level of this structural analysis, advanced structural analysis. Okay, and then this beam supports including the sinking condition. Okay, these concepts we will involve the same combination we will deal with the stiffness method. Again, introduction, application of this stiffness method, stiffness matrix method or stiffness method. Okay, anything is okay. Okay, this is stiffness method to the continuous beam having an highest of two unknowns only and involving the support settlement conditions also. Okay, so this is our whole syllabus. So that's why they have given introduction to the matrix methods involving the main two methods and its basic introductions and its application towards the continuous beams with two unknowns highest, and it is having the sinking condition involvement also. So those cases we will deal. And then the first thing, introduction. Why we are going for the matrix methods? Okay, why the matrix method is coming into our life, which we learned in our mathematical studies. Okay, so the analysis of indeterminate structures is the major field of structural engineering. Yes. So in every structural engineering, or what is the question mark for a structural engineer means what are the forces coming onto this, or what is the bending diagram output, or at which point the maximum shear force may come. So all those things are the next questions for the every structural engineer. Not only giving the cross section, but also they should have to analyze the structure for the given loading conditions. So analysis means the outputs in the form of slopes, or in the form of a displacement, or in the form of some unknown support reactions. So all those unknowns needed to be analyzed. So that is the main question mark coming for the structural engineering. Okay, there are several methods for this analysis. Yes, these all analysis we have done using different methods for different structures. First, simply for the cantilever beam, what we have done for the basic analysis, it is having only one fixed end. Or for the simply support beam, support reaction calculation using the equilibrium condition. Next, we came for the overhang. Same like the simply supported, we have analyzed for the unknown support reactions even in the overhanging beams. Later we came to the proper cantilever beams. In the proper cantilever beams, we came for the analysis of support reaction or the prop reaction answer. So the prop reaction output has been calculated with our things which are we have involved as the analysis of the proper cantilever beam. So calculating the unknown, what is the main unknown that I am calculating. And then in case of the fixed beams, calculating the support moments, calculating the support reactions, what are the main unknowns we are analyzing, and then we are generating the shear force in bending moment diagram. And then for the continuous beams, we have calculated the support moments using the Clapeyron's theorem, and then we came for the analysis of the support reactions and generated the shear force in bending moment. So the complete analysis also done there. So in this way, one method, one structure is having one method. And in a common way, we first started slope deflection method. So that slope deflection method can be applicable for anything. And then we came for the moment distribution method. This moment distribution method also can be used for any indeterminate structure. And then we came for the Canis method. This Canis method is also helping us for analyzing any type of indeterminate structure, even including the frames like the moment distribution method also. Okay. So this moment distribution and Canis are helping us for analyzing the unknowns in framed structure. Okay, so many such type of methods are available for us for analyzing any structure. For hand calculation, the best among those explained so far are Canis method. So, Canis method is generally used because they will not repeatedly go for the calculation. You may think the Canis method is very lengthy. How they are saying this is the simplest? Because they are giving the framed structure and keeping all the things like an Excel. They are giving some output with the replacement of a particular quantity like a contribution factor. So that contribution factor they are removing and changing some other value. So with that replacement, what is the output? That will come as the next output in the Excel. So the Excel output is coming. So they are maintaining the overall spreadsheets, and with the analysis they can easily come out. So this movement, this load in this direction. So all the combinations they can apply and they will generate a single format. So that in hand the Canis method is very useful for us for calculating the corresponding moments and the unknown support reactions. Okay, but this method will not be convenient for the analysis of present day multi-story buildings. Yes, in generally for a 2-bay or a 3-bay story buildings, it is okay, I can develop for the Excel. But when it is coming to the 25-story, 35-story, like those multi-storied structures, firstly, we should have to generate the Excel sheet. That spreadsheet generation itself will take a very long process. That's why for nowadays or in the present day, as we are using so many multi-storied buildings, multi-story means level by level, so many stories were there. So those type of multi-story structures, MSS structures, I can't use Canis method for the longer period. And the need for the analysis of the higher degree intermediate structures and development of the computer have given rise to the new method called matrix method. Yes, so as I am doing the need for the analysis of high degree intermediate structure. So the indeterminate structure is having some unknowns. So that unknown count I call it as a degree of the indeterminacy. So it is having two support reactions as the unknowns. So that is having two unknowns, 2 degree. Or if it is having more unknowns, it's having more degrees. Okay. So as we are going through, we are giving a requirement, we are need. So we are in a need for calculating degree of intermediate structures, higher degree of intermediate structures, and the development of computers also. So here the requirement is rising in one way, and also the computer availability is also rising one way. So that involving the requirement of analyzing more unknowns and using the computer's method involving both the two, we have started a new method, that is matrix method. Okay, basically there are two methods for the matrix method, namely flexibility matrix method and stiffness matrix method. Okay, so we have said matrix method has evolved because I am thinking of calculating the more unknowns at a time with a lesser duration, and also at the same time I am having the help of computers. So involving those two at a time, I can calculate using the matrix method. This matrix method has two methods in it. One is using the flexibility concept. So flexibility matrix method and then the stiffness matrix method. Firstly, the flexibility matrix method. Okay, the systematic development of the consistent deformation method in the matrix form has led to flexibility matrix method. So in a systematic way, when I want to calculate the deformations, okay, so the corresponding consistent deformations I want to calculate in a systematic way. So this thinking has led to the generation of flexibility matrix method. Okay, in this method, what we are doing, the basic unknowns are the redundant forces. So the main unknown in this matrix of flexibility matrix is redundant force. Redundant means unknown forces. Okay, the basic unknowns are the redundant forces. What are the forces? We don't know. Those are my redundants. Those are my unknowns. Hence, the analyst has to identify basic determinate structure and thereby identify the redundant forces. So, from the indeterminate structure, I should have to identify a determinate structure. Okay, so from the indeterminate structure, I should have to make an determinate structure. So that while I am doing the determinate and indeterminate conversion, I can observe what are the redundant forces. Okay, so I should have to identify those redundant forces. Okay, the number of redundant forces is equal to degree of static indeterminacy. how many unknown forces I need to calculate. Okay, the number of redundant forces is equal to the degree of static indeterminacy of the particular structure. So I have said this is an indeterminate structure. Okay, so in this method the basic unknown is, hence the analyst first needed to identify the basic determinate structure. So this is my indeterminate structure and I am converting this to a determinate structure, one end hinge, other end roller, or I can say one end fixed, other end free. Okay, in this way I can make this indeterminate structure to a determinate structure. While doing that, what I have done, once I have made this as my redundant, or once I have made the corresponding moment as the redundant, I have two options. So while making this indeterminate to determinate, I have observed one moment, so that I can, if the moment is not there, this is determinate, or if this support reaction is not there, this is redundant. So this unknowns, what are the extra unknown quantity, either this one or that one, any one method you can choose. Okay, any one method you can choose. So identifying the redundant force. So if I am considering this simply supported end, what is the redundant force? 1. Or if I am considering this way, what is the redundant force? Only one vertical reaction. Okay, that count the quantity of the redundant forces, the quantity of redundant forces which are unknown for us can be called as degree of static indeterminacy. So the degree of static indeterminacy is 1 for the propped cantilever beam. And then the displacements in the basic determinate structure due to the given loading and the redundant forces are found and the consistency conditions are found. So what we are doing here, the corresponding displacements in the basic determinate structure due to the given loading and the redundant forces are found and the consistency conditions are found. Okay, the resulting simultaneous equations are solved to get the redundant forces. Okay, using the concept of displacements, I am analyzing the redundant forces. Then the required quantities at any section can be calculated. So the step by step we are developing and making the indeterminate to a determinate. Then we can get the statical indeterminacy, degree of static indeterminacy of the structure, and the degree of static indeterminacy is helping us, and the displacements in the determinate structure. Okay, the basic displacements in the determinate structure due to the given loading, and also the redundant forces are found with the consistency conditions. So they should maintain the consistency and follow the original structure's condition. Okay, so the consistency conditions are used and the resulting simultaneous equations are solved to get the redundant forces, because my unknown is redundant force only. So for getting the redundant force, we are using the simultaneous repetition of the equations. In this way we can develop or we can analyze. Analyze means calculating the unknowns. Here for me the unknown is prop reaction. So that prop reaction is my redundant force. Okay, that redundant force I can calculate with the conditions. Okay. Next, the equations developed are in the matrix form. So all the equations we have said, we will set a number of equations and those equations we will write it in a matrix form. So how we are writing the matrix form in the equation? Generally you can say 2x plus 3y is equal to 5, 3x plus 2y is equal to 4, or you can write 2, 3, 3, 2 and x, y, which is equal to 5 and 4. How I have written 2x plus 3y is equal to 5, 3x plus 2y is equal to 4. So the equations we have generated and that will be converted into the matrix form. Okay, the equations developed will be in the matrix form. Yes, I can convert them into the matrix form, taking the common variables, taking the outputs on the other side. Okay. this thinking needs some mathematical and some mathematical concept also. Okay. Since the computers can be used for solving the simultaneous equation, there is no limit for the number of equations. How many number of equations you give also, that is, there is no problem. How many unknowns you give also, it will calculate. Okay. This method is known as the force method, flexibility method or compatibility method. Force methods, flexibility methods or compatibility method. Any method is, we call it as this flexibility matrix method only. The next thing, stiffness matrix method. The systematic development of the slope deflection method in the matrix form has given rise to the stiffness matrix method. Okay, so there we have observed for the displacements. Here, slope deflection equations. There the displacements has given me the rise. Okay, so the displacement given me the rise for the redundant force calculation. Here, the output of the slope deflection method, those concept of slope deflection method and its systematic development has given me the rise to the stiffness matrix method. Okay, and in this method, the basic unknowns are displacements of the joints. There the basic unknowns are redundant forces. Okay, that's why that is force method or flexibility method or the compatibility method. Here it is the basic unknowns are displacements. That's why it is the equations of the equilibrium. There forces are the unknowns. Redundant forces are the unknowns. That's why it is a force method or flexibility method. Here the basic unknowns are displacements of the joints. Displacement of the joint. That's why the basic unknown is the displacement of the joint, and that's why I am calling it as a displacement method or stiffness matrix method or equilibrium equation method or equilibrium method. Okay, why it is equilibrium method? See here, the equations of the equilibrium are found and solved to get slopes and deflections at the joint. Okay, the equations of equilibrium are helping. As the equations of equilibrium are helping me, I am using this method as equilibrium method. Okay, using this, moments, shear forces will be calculated. As the slopes and deflections are known, the corresponding moments and shear forces I am calculating. This method is known as stiffness matrix, displacement or equilibrium method. Okay, so this is the another method. There I have observed redundant forces are the unknowns in the flexibility method or force method or compatibility method. In the stiffness matrix method, the main unknowns are displacements at the joints. That's why I am calling it as displacement method or stiffness matrix method or equilibrium equation method or equilibrium method. Next thing, the different approaches in the matrix methods. There are two approaches to the solution of a matrix method. Firstly, direct approach or structures approach. The next thing, transformation matrix approach or element approach. So, whole in a structure we can approach or element wise also we can approach. Okay, direct approach, directly to the structure I am going, or transformation matrix approach. So, element by element I am solving, so I am transforming those matrices, those transformation matrix approach. So, the first one is direct approach to the structure directly. Next one is elemental approach, that elemental is transformation matrix approach. Okay, the first method gives a clear concept of analysis, while the second is ideally suited because I am splitting one by one, right? So, elemental approach I am doing. Okay, that's why it is ideally suited for developing general purpose computer programs for the structural analysis. Okay, so the first method, whole in a whole, direct method or the structural approach method, that is a good method and it is suiting. And also the second method is also okay and suits for all type of the things, all type of the structural analysis using our computers. Since this chapter is an introduction to the method of undergraduate students, only the direct approach is dealt. Only directly to the structure I am dealing. Okay, not in a elemental we are doing, directly to the structure we are doing. Okay, the terms used in the matrix method are explained first, then flexibility method and stiffness method will be taken up. Okay, so here in the introduction of the matrix methods, we are going for the basic involvement, and then direct approach only we are going. Directly to the structure we are going, not in a elemental way. Elemental way means that is the next upgraded version of this thing. Finite element analysis, FEM will be there. Okay, that is the upgraded version of this concept. Okay, and the terms used in the matrix method are explained first. Firstly, what are the words we are using, that will be explained, and then the main flexibility method, main stiffness matrix method we will go. Okay. First word, first new unknown thing is degree of static indeterminacy. This degree of static indeterminacy is a very common word for us even in our structural analysis. There in the first chapter we have given a definition also. So, the number of equations required over and above equations of static equilibrium for the analysis of a structure is known as degree of static indeterminacy or degree of redundancy of the structure. So, how many equations required or how many unknowns are there over the number of equilibrium equations available? The number of equations required over the number of available equilibrium equations. I am having the basic equilibrium equations sigma h, sigma v, sigma m. Over these three, still any unknowns were there. So, for calculating each unknown, I need one equation. So, over the equilibrium equations, how many equations required? The number of equations required for calculating the unknowns over the equilibrium equations available can be called as static indeterminacy, degree of static indeterminacy or degree of redundancy of the structure. Next thing, a structure is said to be kinematically indeterminate in the displacement components of its joints can't be determined by compatibility equations alone. Okay. So, this is static indeterminacy. Next thing is kinematic indeterminacy, degree of kinematic indeterminacy. What is this degree of kinematic indeterminacy? See here, for the structures, additional equations based on the equilibrium conditions must be formulated to obtain the number of equations necessary for determining all the unknown displacement components. So, till now we have observed only for analyzing the external support reactions. Only for analyzing what are the external support reactions. Those support reactions, if I can't calculate using the available equilibrium equation, that new unknown equations required, that count will come into degree of static indeterminacy or degree of redundancy. In case of kinematic indeterminacy, so a structure is said to be kinematically indeterminate. When we call a structure as a kinematically indeterminate, that is statical indeterminacy. So, when the unknown support reactions or the unknowns in the structure are not sufficient for the available equilibrium equation. So, it is having more unknowns. That is statical indeterminacy. When a structure, I call it as a kinematically indeterminate if the displacement components of its joints can't be determined by the compatibility equations alone. So, there I have used equilibrium equations and I can't calculate the support reactions. Then it is statically determinate. If the compatibility equations were there and also I can't calculate the displacements, slopes and rotations, I can't calculate using the available compatibility equations, then the structure I call it as, or we can call it as statical, so kinematically indeterminate. For such type of structures, additional equations based on the equilibrium conditions must be formed. As you already know, so what is the situation of the particular structure or what the component is saying. So, observing all those equilibrium conditions, so involving all the equilibrium conditions, we should have to again determine the unknown displacements. So, again unknowns were there. For calculating the unknown displacements, again I am formulating some equations. As the unknown is there, I need an equation. So, we are formulating some equations based on the equilibrium condition of the particular structure. Okay, so the structure additional equations based on the equilibrium must be formulated to obtain the number of equations necessary for determining all the unknown displacement components. Now, the number of equilibrium equations needed for finding the displacement components of all the joints of the structure are known as degree of kinematic indeterminacy or degree of freedom of the structure. Degree of kinematic indeterminacy or degree of freedom, that is degree of static indeterminacy or degree of redundancy. So in case of degree of redundancy, so the number of static equilibrium equations required, the number of equations required over the available static equilibrium, number of equations required over the static equilibrium equations, that is degree of static indeterminacy or degree of redundancy. Here the number of equilibrium conditions, the number of equilibrium conditions needed for finding the displacements. There I am thinking about the support reactions. Here I am thinking about the inside displacements of the joints. Okay, so displacement components of the joints. So how many number of equilibrium conditions I need for calculating the displacements of the joints is the structure of the structure are known as degree of kinematic indeterminacy or degree of freedom of the structure. Okay, so once you see the example, you can think what the things they are saying. For a beam, the degree of freedom at an end is given by, degree of freedom means how many number of equations for calculating the displacements at the joints. How many number of equations required? How many number of equations are required for finding the displacements at the joints? So, for the free end, there are 3 degrees of freedom because the free end can move in any way. So, for how much it has went in the downward, I need one equation. How much it has went in the horizontal, I need one equation. How much amount it has rotated, so that quantity I need. So, the degree of freedom at the free end is equal to 3. Now, at the simply supported end or the roller end, the degree of freedom is 2. And then hinged end, that is 1. Simply supported means simply it was placed. Simply supported beam was different, simply supported end is different. Simply supported, just it was placed. What it is doing? Again it is doing like a roller end. It is simply stopping like a prop. Okay, so simply supported end. And hinged end it is 1. And for the fixed end it is 0. So how many ways it can go? Those many unknowns will be generated. As the free end can go horizontal, can go vertical, can give the rotation. So it is having 3 degrees of freedom. So 3 degrees of freedom, degree of kinematic indeterminacy, I should have to use 3 equations for calculating in which direction this displacement happened. So in that direction, what is the displacement happened? In this direction, what is the displacement happened? And for the roller end, only for the vertical reaction I am stopping, and it can go in the horizontal, it can give the rotation. That's why the degree of freedom for the simply supported or the roller end is 2. And then the hinged end, as it is stopping in the vertical and horizontal way, only it is giving, allowing the body for the rotation. So for calculating the rotational displacement, I need one equation. So the number of equilibrium equations are required, equilibrium conditions are required for calculating the displacements at the joints. For calculating the displacements at the joints, I need one equation. For the fixed end, as there is no displacement, the degree of freedom at the fixed end is 0. Degree of kinematic indeterminacy is 0. the degree of kinematic indeterminacy, capital D suffix K, we will write it as D suffix K, for one end hinge and the other end roller. So, one end hinge and the other end roller. The degree of freedom. What is the degree of freedom? Here, 1 degree of freedom. Unknowns are 2, but degree of freedom, it can give rotation. What are the degrees of freedom here? Here, the degree of freedom are 2. One hinge, other end roller. Because at the hinged end, 2 unknown reactions are there, vertical and horizontal. But how many ways it can give the displacement? It can give rotation. It is not resisting the rotation. That's why it can give the rotation. As it is showing the displacement, I need one equation for calculating that. Similarly, for the roller, it is giving rotation also, it is giving horizontal displacement also. So, for calculating those 2 unknown displacements, I need 2 more equations. So, the kinematic indeterminacy is through 3, or the degree of freedom for the whole beam is 3. And then, the propped cantilever beam. As the end is fixed, it is not showing any displacement. So, there is no degree of freedom. The degree of freedom is 0 because it is not showing any displacement. There is no freedom for the body. But here, the bumper has a freedom. It was simply a supported end or a roller type end. So, it can move in the horizontal way or it can give the bending. So, this end will have 2 degree of freedom because it is a roller type or simply supported end. So, the summation of these two, the total propped cantilever is having 2 degrees of freedom. And then for the fixed beam, as the fixed beam is having both ends fixed, at left end there is no freedom for the member. How many ways it is having freedom? That is degrees of freedom. In another name I am calling it as degree of kinematic indeterminacy. As it is having the freedom to rotate, in that way I need to calculate the rotation. How many ways it can go in a horizontal? So, it can go in horizontal displacement. So, for calculating the horizontal displacement, I need an equation. Even now, as it is having more degrees of freedom, I need to know more equations for calculating the particular displacement in the direction. Okay, so here the degree of freedom is equal to 0 and for this the degree of freedom is equal to 0. And when you see the structure, so in this way the degrees of freedom, the static indeterminacy and the kinematic indeterminacy were being calculated. Okay, so in the next class we are going for the calculation of kinematic and static indeterminacy for the frames and beams. Thank you.